Hello and welcome back to another episode of Math with Sohn. Today we are going to be figuring out a little bit about air resistance in relationship to the AICE Physics exam. So for AICE Physics, there are two things that they like you to know with air resistance. They want you to know that it is proportional to velocity squared, which the velocity squared sometimes matters. Sometimes you can get away with the fact that if you're going faster, you're going to have more air resistance. So sometimes you can get away with just that simple fact, but it is really proportional to velocity squared. And I'll show you why sometimes the velocity squared matters, but it's about 50% of the time it might matter. All right. The other thing that AICE cares about is if you have more mass with a similar shaped object, as long as it is a similar shaped object. For instance, if you have two balls and one's a bowling ball and one's a basketball, the thing with more mass will have a faster terminal velocity, which means it will land quicker because it will end up going faster in the long run than the basketball would. But why is that? Why is that? And the important feature to why that is, let's say I have a very big mg here. So this is my bowling ball. And then we have force drag. It would also have to be, in order for this to reach terminal velocity, these would be equal. And in order for those to be equal, the force drag, because it's proportional, that's what this symbol means, to velocity squared, I will be able to be going faster than if I have a tinier or a smaller object, like a basketball, doesn't weigh as much. It is going to have a smaller mg, and therefore a smaller force of drag, and therefore will have a smaller or a lower valued terminal velocity. And that is why that smaller objects end up not going that fast. And if you drop a feather, it kind of flutters to the ground, versus if you dropped a steel feather, the same exact feather, but if you dipped it in gold, it would fall just straight to the ground because it wouldn't reach terminal velocity. Okay? So another thing that could happen with this is you could be expected to draw a position versus time graph, a velocity versus time graph, or an acceleration versus time graph. Okay? So you could be expected to draw those three things. And a lot of times for AICE, when you're drawing them, they draw just a magnitude of it, not an actual value of it. So for instance, for the position, they assume that when you start, you're at position 0. But technically you're in the sky, so this might be different if you're in the sky. So I'll do maybe two versions of this to see like the subtle things. So if it was position 0, what's going to happen in the very beginning? Well, you're going to start falling out of that, the ball would start falling out of the airplane, and it would not be moving very fast in the beginning because gravity hasn't had an opportunity to speed it up. So it is going to be a parabolic shape. And then as gravity speeds it up, it is going to look something like that, where it's going to get faster and faster and faster because gravity is going to speed it up. But air resistance is going to slow it down. And once air resistance slows it down enough where mg is equal to that force of drag or force of air resistance, then it will be moving at a constant rate, and therefore the position will just go up linear. Now, I've exaggerated this. That's not actually what it would look like. What it would actually look like would be a little bit more subtle, where that curves up, and then it continues at that moment at a linear rate from there. But that doesn't show up as easily for understanding the concept. So it's parabolic, then linear. This one's the accurate graph, and that one is the exaggerated graph. Velocity versus time. Well, what's going to happen to the velocity? Well, the velocity, again, the bowling ball fell out of the sky, out of the airplane. It starts with a velocity of 0, okay? And it will increase, okay? It will increase, but it's going to have to slow down because air resistance is going to affect it. And because air resistance is going to affect it, it's going to kind of curve. It's not going to be linear. We have a changing velocity here. So it'll curve and then eventually get to 0. So this is curved. I didn't do a great job curving it. Curved. And it will be concave down. So it'll be slowing down and then getting to 0. So it has to slow down. It starts at 0, will increase, but it has to slow down how quickly it is increasing its speed. And then we'll have that terminal velocity of whatever it is. So it'll stop and have that max speed. All right. The acceleration graph gets a few people because acceleration doesn't start at 0. Look at the slope of this velocity graph. The slope is big, and then the slope slows down. So because the slope is big in the beginning, we're going to start here because that actually makes sense. We're going to start with gravity, and we're doing magnitude, so positive 9.81. And then it will have to finish with a net 0 acceleration. So this is going to have to go down in some way. The question is it going to go down linearly? Is it going to go down quadratically? And remember, the velocity squared is essentially equal to force of drag. So it's going to have to be parabolic. And because it's parabolic, it's going to be like so. Where we're going to be at 9.81 for a bit because we're going to start out really slow. But then eventually that curve will end up becoming more and more rapid, and therefore the slope will become more and more closer to 0 for that. Okay? So those are the regular magnitude graphs. If we did a position graph that was accurate for y position, it would start up at the top, and it would just be kind of the flip of this, where the slope here is starting out 0, and then it would go down at a constant rate. Okay? Same thing would happen with the velocity, but the velocity starts at 0, and it would curve. It would speed up, and then it would curve, and then it would slow down right here. And then for the acceleration, it would still be negative. It would just be negative 9.81, and it would be just the flip of that. That one's actually, these two are just flipped. This is kind of flipped, but it's flipped and shot up. Okay? So that's going to do it for this one. I hope you have a slightly better understanding of air resistance. Until next time, stay positive, my friends, and I will see y'all later. Bye.